Hi everyone, welcome to the Machine Learning with Python. The last class, this is on unsupervised learning, clustering, and our expert Jaymeet Vasava will walk you through the difference between classification, clustering, and the various methods used in clustering, etc. And this will be the final class, and we wish him best of luck because he plans to start private classes. He has been volunteering for 6 months. We are very grateful to Jaimeet for having led the study circle, and this will be the last class on machine learning with Python. And I will hand over to Jaimeet to present and share whatever lab notebooks he has got, which he wants to present today. And best of luck to him. Jaimeet, take over. We are handing over to you. Thanks.
So thanks a lot, sir, for the introduction. And hello, everyone. This is Machine Learning with Python, session 7, which is on clustering. So let's get started with clustering. So first of all, the learning objectives or the goals for this session. We will discuss about clustering and their importance in analytics, learn different types of clustering techniques, how clusterings or how the clusters can be measured, and what are the different measuring methods in it. Then what are the optimal methods if we are going to create certain clusters, and of course there has to be a balance between not too much and not too less. So what would be the optimal number of clusters in the data? So that we'll be finding how we can find the most optimal number of clusters, and we'll all be doing this with the help of scikit-learn, a library of Python, and Seaborn and Matplotlib. So let's get started with clustering. First, we'll look at some of the ML categories in order to get to clustering. Before getting to clustering, the ML categories, this is something that we have used again and again in order to have some of the highlights before getting to the main topic. So we have ML categories, we have supervised learning, unsupervised learning, and reinforced learning. Supervised learning having the outcome known prior to us, and we are trying to measure the model's prediction and decide how much the model has predicted compared to the actual outcome. Then in the unsupervised learning, the model has to learn the data on its own, and there is no a known outcome, and we let the model learn the pattern and tell us what the data is telling. In reinforced learning, it's a penalty and reward based learning. If the model predicts good or desired results, it is rewarded and penalized if not so. Then for supervised, we have classification, a picture of a cat being recognized in a picture is a classification. If there is a class or not, then it becomes a binary classification. And if there are more than one animal in the picture, it becomes a multi-class classification. Then regression is for continuous values to predict a house price based on the area, the gradient of the house, and so on. Then for unsupervised learning, we have clustering, association, and dimensionality reduction. As we are going to discuss clustering, I'll cover association first right now. So association is nothing but creating an association with for one item to another. So in supermarket, going for a particular kind of shopping, let's say breakfast, if we buy milk, then bread can be recommended for milk. And as we are creating association of bread with the milk being purchased, so that becomes association. Then dimensionality reduction is is a dimensionality reduction. It is a technique of reducing the number of features in the data set while keeping the originality of the data set. So the model has to learn a few features, uh, a few less features, and still have the potential to give uh, learn the data. Then comes clustering. So clustering is nothing but grouping of similar data points or records or observations together, and and telling which are the similar and which one are the dissimilar based on the distances where they are mapped. So we'll start with clustering. So we'll start with discussing few of the definitions from some of the popular platforms for learning. We'll start with GFG, or a Geek for Geeks definition on clustering. The task of grouping data points based on their similarity with each other is called clustering or cluster analysis. This method is defined under a branch of unsupervised learning, which aims at gaining insights from unlabeled data points. That is, unlike supervised learning, we don't have a target value. For data camps definition, clustering is the process of arranging a group of objects in such a manner that the objects in the same group are, which are objects in the same group or clusters, are more similar to each other than the objects in any other group. Then for developer.google's definition, grouping related examples, particularly during unsupervised learning. Once all the examples are grouped, a human can optionally supply meaning to each clusters. So from a data set, the clusters have clusters based on the different features have been different features are present in the data set. Certain features are common among the records, and based on those similarity, and the clusters have been formed. And we can then name or give uh, an intelligible meaning to the clusters. Then, according to IBM, clustering is an unsupervised machine learning algorithm that organizes and classifies different objects, data points, or observations into groups or clusters based on similarities or patterns. So, clustering compared to classification. So clustering is an unsupervised technique, whereas classification is a supervised technique, as we have a labeled data or a known outcome. Whereas in clustering, we have unlabeled data and we don't have an known outcome. Clustering is a descriptive analytics, whereas classification is a predictive analytics. Descriptive analytics focuses on past and understanding what has happened, whereas in predictive analytics, we learn the past data in order to predict the future data. Then the main intuition or the reason or the in, or the way of working of the clustering is to create heterogeneous groups or clusters, and having those each group containing a homogeneous or same or similar kind of records. So how can we use clustering? So we will understand this with the help of a company who is trying to increase its brand awareness. So it will design a campaign in order to do that. So will designing a single campaign solve a company's problem, or will it need to design a single campaign in a way that can serve multiple uh, users? or it designs some multiple campaigns in order to cater to the uh, desired group, to target the desired groups. So for understanding this uh, companies increasing of brand awareness, we'll take an example of an automobile company, tech company, and a skincare company. So an automobile company will try to identify different segments within its industry for luxury sedan enthusiasts, eco-conscious millennials, and rugged SUV fans or users. Then for a tech company, target segments like tech enthusiasts would love to have smart devices, productivity focused professionals, and older individuals would like to have a really simple user friendly interface to use the technology. Then for the skincare company, a company offering skincare products can segment customers based on skin type, age, concerns, and preferences such as oil acne prone teenagers, as teenagers do have some kind of changes happening in the body, which also reflect onto their skins. So oily or acne prone teenagers, and then anti-aging middle-aged groups to protect their skin from uh, skin skin or having a lesser effect of aging, and having, and the other segment can be the sensitive skin individuals. So the companies have to know how many customer segments exist and which customer falls under which segment. So clustering as a technique can be used here to address the situation. So you can see that for car, luxury sedans, eco-conscious millennials, and SUV users, they form their own clusters. For the tech company, the tech enthusiast, productivity focused professionals, and older individuals, they create their own clusters. Similarly, for skincare, the teenagers, the middle-aged group, sensitive skin individuals, they form their own clusters. So this is how the clustering is helpful to the company, and can be used in order to get a better insight. So how clustering works. It helps data scientists to create a homogeneous group of customers for better management of customers. In many analytics projects, once the data preparation is complete, clustering is usually carried out before applying other analytical models. Clustering is a divide and conquer strategy which divides the dataset into homogeneous groups, which can be further used to prescribe the right strategy for different groups. In clustering, the objective is to ensure the variation within a cluster is minimized when the variation between cluster is while the variation between the clusters is maximized. So a simple example of clustering you can see in a 2D space, data points have been mapped on a 2D space, and you can see that there are certain data points closer to each other marked with different colors, whereas others are marked with uh, different colors, and the certain clusters have been formed depending on the distance of the data points from each other. For one cluster, the certain data points will fall under certain distance, and so on. So clustering algorithms use a different distance or similarity or dissimilarity measures to derive the different clusters. Then the type of a distance similarity measure used used plays a crucial role in final cluster formation. A larger distance would imply that observations are far away from one another, whereas higher similarity would indicate that the observations are similar. Closer distance basically meaning higher similarity, larger distance meaning less similarity or not similar at all. So by the way, it's not about a higher similarity, higher distances having no similarity. As whenever we are trying to map certain data points, they have to fall under certain things in order to have that. But it basically means that the observations have a higher dissimilarity. That's it, not no similarity. So excuse me for that. So we'll learn about clustering with the help of a data set which contains the information of uh, customers' age and their income. So we'll use the income data set. We'll first input pandas for reading it and then printing the first 5 records of the data set. And you can see how the first 5 records look like, the income and the age being showcased. So to understand how the whole data set would look like, we would uh, use a scatter plot in order to understand what is the relation between the age that is present in the database data set and their income and how they look like when they are plotted on a graph. So we'll use the needed library, we'll import the needed libraries and then plot the graphs, plot the graph using the data. So when we plot the graph, this is what the graph would look like, as you can see on the right side of the screen. And you can see that certain clusters are formed. We can see that there are 3 clusters being formed, and just roughly pointing out those clusters or informally pointing out those clusters, you can see that one is a low age, high income, which is on top left, then low age, high income, which is on top left, medium age, medium income on the bottom side of the graph, and uh, higher age and higher income on the top right of the graph. So you can see that there are 3 clusters that are formed from the database. So, so as we discussed about the distances uh, used in order to measure the similarities. So finding the similarities using the distance in the clustering techniques. So clustering techniques work under certain assumptions. Like regression analysis assumes that a linear relation between the independent and there is a linear relationship between the independent and the dependent variable. The collaborative filtering assumes that the users with similar preference in the past will have the similar preference in the future also. So just to brief a bit about collaborative filtering, assume that you are watching a video on YouTube, and when you like the video and a user like you also is liking the same video, you both of the users will be recommended with a similar kind of content based on liking that one same video. So this is what the collaborative filtering means. So collaborative filtering assumes that when you have liked that video, it will recommend similar kind of videos for your future views or future viewing. So it assumes that your present and the past preferences are also going to be same for your future preferences. Of course, it has its own way to deal with the future issue, and it manages itself and changes for the future preferences. But collaborative filtering works under that assumption. So the same way, the clustering techniques work under the assumption that the subsets in the data that are similar or homogeneous. It works under the assumption that there are subsets in the data that are similar or homogeneous. So one approach for measuring similarity is through distances measured using different metrics. So first is a Euclidean distance. Euclidean distance is a very common distance. You can see the image on the top left. It's the most in the graph whenever we want to calculate a distance in the graph with the help of x and y coordinates. And this is the distance, Euclidean distance that we use to calculate. So it's calculated by square root of x2 minus x1 whole square plus y2 minus y1 whole square. So the same way for our data sets, a Euclidean distance between two observations, x1 and x2 with n features can be calculated with d of x1, x2 equals to square root of summation of xi1 minus xi2 whole square, where xi1 is the value of the ith feature for first observation and xi2 is the ith feature for the second observation. So with respect, applying that formula with respect to our data set, or formula or the Euclidean distance can be calculated with age 1 minus age 2 whole square plus income 1 minus income 2 whole square, and all of that under a square root. So uses of the Euclidean distance commonly used in clustering algorithms such as k-means and in dimensionality reduction techniques such as principal component analysis, PCA. The advantage of Euclidean distance is simple to understand and calculate, works well when the data attributes are on the same scale. We'll talk about this being on the same scale further when we discuss this. So other distances like Euclidean distance that can be, or metrics, other distance metrics that are commonly used in ML for a different kind of uses are Minkowski distance, which is a generalized distance measure between two observations, and then Jaccard similarity coefficient. It is measurement used when the data is qualitative, especially when attributes can be represented in binary form. Qualitative, you can say that it's a categorical kind of data. Then cosine similarity, in this x1 and x2 are two n-dimensional vectors. If it measures the angle between the two vectors, thus called as vector space model. Then Grover's similarity coefficient. It is used when both the quantitative data and the qualitative data are present as features. Quantitative data is nothing but measuring the heights and continuous kind of values in a way. So starting with the k-means clustering. K-means clustering algorithm is a non-hierarchical clustering method where the number of clusters, which is denoted by k, is predetermined before running the algorithm. So non-hierarchical clustering, also known as partitional clustering, the data set is divided into a fixed number of clusters without forming a hierarchical structure. In hierarchical clustering method, where clusters are nested within one another, non-hierarchical methods create distinct separate clusters. About the k-means algorithm, it's one of the most popular non-hierarchical clustering algorithm. It partitions the data into k clusters, where each cluster is represented by its centroid, which centroid is basically the mean of all the data points in that cluster, or the cluster's mean. The algorithm iteratively assigns each data point to the nearest centroid and then recalculates the centroids based on the mean of the data assigned to each cluster. So number of clusters. So in k-means clustering, the number of clusters is determined before running the algorithm. Unlike hierarchical clustering methods like agglomerative or divisive clustering, where the number of clusters is not predetermined and can be determined based on the structure of the data, k-means requires the user to specify the desired number of clusters. And determining the appropriate value of k often involves a domain knowledge experimentation or using techniques such as elbow method or silhouette analysis to find an optimal number of clusters based on the characteristics of the data. A priori decision is a priori means the decision regarding the number of clusters is made before running the clustering algorithm. This decision is typically based on the requirement of the problem or analyst understanding of the data. So choosing the number of clusters is of course crucial, and it's important as it directly impacts the interpretation and the effectiveness of the clustering results. So we'll be implementing k-means with the help of scikit-learn.cluster. Scikit-learn.cluster will be using the three clusters as when we plotted the graph, we found three clusters, so we'll go with three. We'll fitting our clusters model, and these are the parameter values you can see, and we'll be assigning cluster IDs based on the clusters that the particular observation belongs to. So after assigning the cluster IDs to our clusters with the help of the customer DF that we have created while reading the data set, the labels that were created are 0, 1, and 2. So you can see when on the side of income and age, a new cluster ID column has been added, and you can see the belonging cluster label of each record, of what each record belongs to. So the very first observation belongs to the first cluster, then second or index 1 belongs to a second cluster, index 2 belongs to the first cluster again, and the 3 and 4 belongs to the 0 cluster. So now we'll be plotting the graph with the help of different with the help of cluster IDs, and to set them apart, we'll be using the symbols in order to while plotting them. So it's easier for us to see the observations. So when we plot that with the help of the symbols and the cluster IDs, you can see the observations, how they are plotted. So regarding the clusters that are plotted over here, there is a kind of issue, which is the clusters are mostly segmented based on the income. So when I say that, what I mean is that the salary is on a larger scale compared to the age. So the scale of the age is from 0 to 60, but the scale of the salary is from 0 to 50,000. So in order to get both of these values under a single scale, we have to normalize these values. So we'll be using the normalization over here. So for us, we have the range of age is 0 to 60. The income range is 0 to 50,000. So when we calculate the distance between the data points for clustering, the large differences in income overshadow the difference in the age because the income values are much larger. So the reason to normalize is without normalization, the clustering algorithm mostly uses income to determine clusters because income differences are numerically larger. For example, an age difference of 50 for ages 20 to 70 is significant but appears small compared to the difference in income of 1,000, which might not be significant in our case. So we transform the age and income values in under a common scale of 0 to 1, normalization basically. So after normalization, both age and income differences are equally considered. This allows the clustering algorithm to identify patterns considering both age and income rather than just being dominated by the income differences. So for normalized features, x normalized equals to xi minus x bar divided by sigma x, where x is the mean, x bar is the mean of x, and sigma x is the corresponding standard deviation for the x feature. So for normalizing this in our Python implementation, we'll use scikit-learn.preprocessing and then use the standard scaler. So uh, we'll import standard scaler from the scikit-learn's preprocessing and have a scaled customer DF. And when we get the output of the first 5 values, you can see that the normalized value over here. So after that, we plot the graph again for the these are normalized values. So this is what the graph would look like compared to the graph, this one. This is how the graph looks right now. So after that, when we when we try to get the centroids of the cluster of these clusters, or so we can get the centroids of these clusters using the cluster underscore centers underscore, and get the values in terms of this array. So these these are the standardized values of the clusters. So we can calculate the cluster centers from the original data frame using the information which customers have been allocated to which segments. So so interpreting the clusters. So centroids are mean of the observations, and so they explain the characteristics of the cluster and help us interpret the cluster. So basically, centroids explain what normally the cluster is trying to represent. So in our case, the cluster center or the centroid provides the average age and average income of each cluster. So the customer's age and income will vary with the cluster centers and is called the cluster variance. So we, we first group by using the cluster ID that we have created, and then aggregate with it with the help with the mean and standard deviation, and reset the index back to the original one. So when we print this customer DF, you can see the age and income mean and standard deviations. So for cluster ID 0, the mean is a mean or the age is a 31.7 years, and the income is 54.6K For cluster ID 0, we have the at age at 39.1 years and income at 18.1K. Then for cluster ID 2, we have 46.4 years of age and 43.0 or 43K of income. And you can also say the cluster 0 as a low age and high income, cluster 1 as a mid age and low income, and cluster 2 as high age and medium income. Now we'll be discussing another topic called creating product segments using clustering. So for this, we'll be taking another data set and another example. So this time we'll be taking an example of a company uh, who wants to launch a new beer brand. So what would be the company's objective before launching itself? First, it has to understand the existing market and which products serve which existing segments. We have already talked about the existing market and the existing segments that companies have to first learn about. And to understand the segments, the company collects specification of few samples of beer brands. So, and those uh, just a second. So we'll use the dataset beer.csv that the brand will be using in order to understand the customer segment and what each of the uh, contents of the beer and how it and other information regarding the beer and how it affects the segments. So first, reading the data set and creating the data frame BRDF and printing the BRDF. You can see a snapshot of it on the right. We have 0 to 19 brands, and you can see the calorie count, sodium and alcohol measurements, and the cost of them. So we'll first normalize these values as we have we for the past example we just used normalized. Later on we will do it now. So we'll normalize these values and so, so there are more features, and as the feature increases, it can become more challenging to visualize. So like last time, after normalizing, we created the scatter plot on the graph for the clusters to be visualized. If this time we have a lot of features, and as the more and more features increase, it becomes harder for us to visualize these features from the data set. So for high dimensional data, there are different techniques for discovering or plotting or understanding the data set. One is dendrograms and another one is elbow method. So starting with dendrograms, they are key visualization tool for hierarchical clustering. They display the arrangement of the clusters produced by the hierarchical clustering algorithm. Each merge in the dendrograms present a potential cluster. To make a dendrogram, we'll use the cluster map method from Seaborn. So we'll use Seaborn and call our dendrogram as CMap. give it the assign it to the needed parameters, and this is the dendrograms that it creates. Remember that we had 0 to 19 uh, uh, observations or indices to represent the different brands. So you can see on the image on the right, on the very right, we have those numbers, and depending on the distances from each other, we can talk a bit about the similarity and the dissimilarity. So when we talk about the similarities, the observation or the record 16 and 10 have the most similar kind of observations. So when you see the dendrograms on the left side of the dendrogram, you can see that there is the smallest distance that is captured by uh, of the dataset records is for 16 and 10. The other ones are a bit larger and keeps getting larger. So some of the observations from the dendrograms dendrogram reorders the observation based on how close they are to each other using Euclidean distance. The tree on the left of the dendrogram depicts the relative distance between nodes. The, as I said, the similarity of observation or the observation 10 and 16 is very similar, whereas for 2 and 18, which are the farthest apart from each other, are the have the most difference. So we'll look about those the most similar and the least similar records. So when we print the information regarding the 10 and 16 and 2 and 18 being the most similar and the less similar, you can see the similarities in the calorie, sodium level, alcohol level, and the cost, uh, and the differences are for the observation 2 and 18 for the same. So, so the brand low and true have a very low alcohol content, uh, which can uh, which can indicate that it is an outlier and can also be dropped. So, so the tree structure on the left of the dendrogram indicate that there may be 4 or 5 clusters in the data set. So you can see the tree kind of structure that it forms, and you can see the kind of clusters that it can create. So based on that, you can have a rough guideline on how many clusters the data set can contain. So the actual can be determined by creating and interpreting. So actual number of clusters can be determined by actually creating the clusters and by interpreting them. So we'll move further with 4 clusters, as having more clusters can also increase the complexities. So finding optimal number of clusters or the K value using the elbow curve method. This is the second method after after the one that we just discussed using the dendrogram. Uh, so elbow method helps to determine the optimal number of clusters by plotting the explained variance as a function of the number of clusters. The elbow point on the plot indicates the optimal number of clusters. So in context to our case, if we assume all the products belong to only one segment, then the variance of that cluster will be the highest, as each and every brand will be under one cluster, and there will be very high variance. And as we increase the number of clusters, as we keep the brands keep on dividing the brands on more and more clusters, the total variance of all the clusters will start reducing, but the total variance will be zero if we assume that each and every beer brand that is present on the data set has its own cluster. So there has to be a sweet spot between having not too many clusters and having uh, a good variance, or the percentage of variance being explained. So elbow curve method considers the percentage of variance explained as a function of the number of clusters. So the optimal number of clusters is chosen in such a way that adding another cluster does not change the variance explained significantly. So the WCSS is the sum of distance of each point in the cluster to the center of the cluster across k clusters. So for the records of uh, x1 to xn, where each observation uh, is a d-dimensional real vector, k-means clustering algorithm sequence the observations into k sets S, where, uh, for a uh, for sets S1 to Sk to minimize the within cluster sum of squares. So mathematically, the WCSS can be uh, represented as a hard minimum of summation of Si equals to 1 to k, and for xi belongs to Si, the mod of xi minus mu I whole square. So the percentage of variance explains tells us how well the clusters capture the patterns in the data. Adding all the data in one cluster will result in a lot of variations. So adding too many clusters won't explain much additional variance because the big patterns have already been captured. So the increase in explained variance starts to slow down. So we plot a graph of the number of clusters against the percentage of variance explained. So at first the graph will rise steeply, and then it starts to flatten out. And the point where it starts to flatten out forms the kind of bend of or elbow in the graph. This bend suggests that the adding more clusters beyond this point doesn't give you much extra explanatory power. So the elbow criterion helps you choose the right number of clusters by looking for the point on a graph where adding more clusters doesn't significantly improve how well your clusters explain the patterns in your data. So using the elbow method, we'll create the cluster from range 1 to 10 and observe the within cluster sum of squares in each cluster. How marginal gain is explained variance starts to diminish gradually. So for the k-means cluster, the inertia parameter provides the total variance of the particular number of clusters. So we'll, with the help of for loop, we'll loop through 1 to 10 and get those parameters using the inertia. And when we plot the graph, you can see from 80 of on observation 1, on observation 3, the curve starts to flatten out. So we can use 3 or 4, both of them. So, but for now, we will go with the cluster value of or case value as 3. And as also mentioned before, we use these methods in order to have a which serves as a guideline for us. So we can so there is no strict policy to follow them, but rather use them as a guideline and choose the best for us. So for now, we'll be going with 3. So normalizing the values that are used in the BRDF, then creating clusters using case value as 3, and also creating the cluster ID for and giving them the or assigning them with needed labels. So you can see the BRDF now contains a cluster ID and the first, and printing the cluster ID equals to 0. These are the brand names uh, that show up with their respective indices. So some observations regarding cluster ID equals to 0 for the cluster ID 0. The beer with medium alcohol content and medium cost are grouped together, and they may target the largest segment due to their medium cost and medium alcohol content. Similarly, for a cluster ID 1, all the light beers with low calories and sodium content are clustered into one group. This must be addressing for some of the calorie conscious customers that the brands serve. And for cluster ID 2, these are some of the expensive beer brands which have a high alcohol content, low sodium content, and the target customers are the ones which are sensitive to the brand's image, and they are promoted as some of the premium drinks or premium beers. So now we'll discuss hierarchical clustering. So according to GFG or Geek for Geeks, in data mining and statistics, hierarchical clustering analysis is a method of clustering analysis that seeks to build a hierarchy of clusters, that is, tree-type structures based on the hierarchy. So you can see the alphabets themselves. This type of clustering is called agglomerative clustering. So you can see that all of the alphabets being grouped together at the end, while each of them were their own each clusters at the beginning. So the steps to follow or build this agglomerative clustering: consider each alphabet as a single cluster and calculate the distance of one cluster from all the other clusters. In the second step, comparable clusters are merged together to form a single cluster. So cluster B and cluster C are very similar to each other. Therefore, we merge them in the second step, similar to cluster D and E. And at the end, we have A, B, C, D, E, and F. So repeating these steps, we find the clusters D, E, F, and B, C are comparable and merged together to form a new cluster. And now we are left with clusters A and B, C, D, E, F. And at the very end, the two remaining clusters are merged together to form a single cluster. So for agglomerative clustering, we'll use scikit-learn's agglomerative clustering and understand that. And this agglomerative clustering can also be understood through the dendrograms that we have used before. So for this hierarchical clustering, we'll use the edge clusters as our model and fit it, and then create the edge cluster ID with its label for the hierarchical clustering. So we'll have the cluster ID as well as edge cluster ID, and we'll see how the result. So when we use it for the edge cluster ID equals to 0, and this is what the edge cluster ID for 0 looks like, and the corresponding cluster ID is 1 for this. Then for edge cluster ID 1 and edge cluster ID 2, the corresponding cluster ID is 0 and 2. So apart from a bit of interchange of cluster ID 0 and 1 and 1 and 0, there are nothing that is different, and there is so the hierarchical clustering is grouping the same kind of brands with just only the difference being the cluster IDs. So you can see in cluster ID 2, the cluster IDs and the edge cluster IDs, both of them are 2. So, so now we'll summarize this session. So we start with discussing clustering with the data set called income data, where we had the income and age of the customers. So in order to get a deeper insight into the data set, we plotted the data set on a scatter plot with these needed libraries. We plotted the graph, and this is what the clusters look like. So there you can see, roughly speaking, there were 3 visible clusters, very easy to see and recognize. So we went with k-means cluster of or the case value of 3. And when we made the model, and so these were the parameter values for the model that were being used. And then we added an additional column into the data frame, a cluster ID, and give it the needed or the respective labels. And these are the first 5 records of the data frame with cluster ID 0, 1, and 2. Then plotting these customer segments with these cluster IDs and using the symbols over here. This is the graph that we get. And you remember that we talked about normalization and getting an income being more dominated when while being plotted on the graph. So we normalize the values of income and age, both of them. These were the values of the scaled values of them. And we created a new cluster ID and then normalize those values. And this was the graph for the normalized values of the age and using the age and the income of the customers. And to get the centroids of the clusters, this is cluster underscore centers underscore were used in order to get the clusters of or the centroids of these. Now understand as centroids, they represent the mean. So the mean also represent in a way the characteristics of the cluster. So when interpreting the clusters, we we use the cluster ID, age, and income, and their standard deviation and their mean and standard deviation. So you can see that according to the cluster IDs for age group 0, the cluster ID 0, the mean was 46 years, and the income mean was 43K. For cluster ID 1, the mean was the age mean was 39 years, and income mean was 18.1K. For cluster ID 2, the age mean was 31 years, and the income mean was 54K. After that, we discussed the segments segmentations in the market, and we discussed an example of of a company entering as a new beer brand. And to understand the segments in the market, it uses this beer data set, which is from which is from starts from 0 to 19 records, or in terms of indices. So we standardize the values of the data sets, and with the help of a dendrogram, we visualize the data set. So you can see that over here, I hope you can see the cursor, that these are, and this is the this is the most similar observation, which is 16 and 10, and this 1 and this 2 and 18, as they are have the most distance, they become the least similar observations. So to know the differences, we print the respective observations of 10 and 16 being the similar ones. You can see the numbers over here. They fall into very similar categories, whereas for 2 and 18 being the least similar, you can see the numbers which are pretty different. Then we discussed about the elbow method, and we we plotted a graph, and from where the graph starts to flatten out, and that we saw as the optimal value for our K, for the number of clusters to go with. So we went with a cluster number as K equals to 3, and so for this we normalize the values of them, and then we use K equals to 3 for that cluster BRDF, and created the cluster ID for assigning the labels. And when we assign the labels, this is what the cluster ID looks like, for starting with 0. And they do show certain kind of similarities between them. Medium alcohol content and medium cost price. For cluster ID equals to 1, they have a low alcohol content and low calorie value. A medium alcohol content but low calorie values. And for cluster ID 2, for the premium branding of a high alcohol content, as well as brand sensitive people. For brand sensitive people who prefers a certain kind of brands for themselves. So after that, we discussed about the hierarchical clustering using the agglomerative clustering of clustering, and we implemented it using the scikit-learn's agglomerative clustering. We created the edge clusters for our model, and also created the additional column for the needed labels, or the assigning the respective labels, not needed, assign the respective labels. So for the edge cluster ID 0, this is what these are these are the records that show up for edge cluster ID 0, and the respective cluster ID is 1 for here for that. And for edge cluster ID 1, this is what the normal cluster ID 0 is, the corresponding cluster ID. And for edge cluster ID 2, the corresponding cluster ID is also 2. And most of the observations are, or all the observations are same. So both the hierarchical clustering is also dividing the clusters based on the same logic as the cluster IDs we have used. So yes, this was it for clustering. These are some of the references that were used in order to make this session. And also we have an announcement to make.
Jaymeet, hold on. Can
Yeah.
you go back to the last slide? Yeah. So this is for Q&A. So thank you, Jaimeet, for the entire course organization as well as delivery of the PGD-AI course. And those who have any questions, please send uh, email to infoATOTFDOTin if you have any questions regarding the course and what Jaimeet conducted. Now, I had asked Mr. Gokhale, our president, to join. Looks like he's not able to join. So what I'm going to do is, on behalf of EOTF, uh, can you change the slide? Next slide. Yeah. So on behalf of the Emerging Open Tech Foundation, we would like to award the certificate of PG Diploma in AI Trainer. This certificate is awarded to Jaymeet Vasava for organizing and conducting EOTF PGD-AI 2024 online training successfully for the calendar year Q2 2024. Uh, this was hosted and organized by EOTF, and Jaimeet was the course instructor and trainer. So we congratulations to Jaimeet for having successfully completed the almost a 3 months course, which started with C, followed by the before the C it was the study circle, that is AIML Design. After design it was C, and then after that it was machine learning using C, data structures and algorithm, and finally the what you call machine learning with Python. And so this was a really great course, and it was targeted towards CDAC as well as any JEE joint entrance exam. So you have entire series of what you call the YouTube videos which are available, more than uh, 35, 30 to 35 classes which he conducted over a period of almost 8 to 10 weeks, I believe. So 12 weeks, usually 3 months. So we congratulate and thank you, Jaimeet, for taking the time to deliver voluntarily the courses. And we are happy to award you this certificate. And now, for a change, I would like you to pitch for yourself. Here is the next slide. Go ahead.
So yeah, thanks a lot for the help. I really learned a lot and got a really good exposure. So thanks to EOTF for giving me this opportunity to take up this position first of all. And Yeah, there is another announcement that I would like to make, that there are this was the sessions that were conducted were targeted at certain kind of topics, but I'm also planning to have private AIML classes, which will be starting at 1st July 2024. So if people are interested in joining the private AIML classes, you can contact me with this email, and uh, we'll be starting at July. So you can contact me before that in order to get the needed info.
Thank you, Jaimeet, and best of luck for the AIML classes. You're starting first July first week, and I think we will close the recording, stop the recording, and then I'll uh, end the call today, and we'll talk later. Okay. Thank you very much. I'm going